Sources of error in DSP implementation and queue notation. Sources of error in DSP implementations. Digital signal processing (DSP) is a use of digital processing, such as by computers or more specialized digital signal processors, to perform a wide variety of signal processing operations. The digital signal processed in this manner are a sequence of numbers that represent samples of a continuous variable in a domain such as time, space, or frequency. In digital electronics, a digital signal is represented as a pulse train, which is typically generated by the switching of a transistor. Theoretical DSP analysis and derivations are typically performed on digital time signal models with no amplitude inaccuracies, that is quantization error, created by the abstract processes of sampling. Numerical methods require a quantized signal, such as those produced by a ADC. The processed result might be a frequency spectrum or a set of statistics, but often it is another quantized signal that is converted back to analog form by a digital to analog converter, that is DAC. Digital signal processing is a core to manipulation, presentation, and/or transfer to various forms of analog signals. Coupled with the recent trends in technological advancement, it has become inevitable to overlook the importance of processing of digital signals to analog and vice versa. Inaccuracy depends on number of factors contributed by ADC and DAC and how the calculations are done in DSP devices. Since different computer arithmetic implementations may respond to overscaled supply voltage very differently, it is highly desirable to develop a method that can quantitatively reveal the transient error characteristics of various computer arithmetic implementations. Although brute force circuit simulations can serve this purpose, it suffers from very high computational complexity, even for small circuits. This makes it impossible to explore computer arithmetic design space over a wide range of VOS by relying on circuit simulations, and hence demands analytical techniques that can efficiently estimate the transient computation error characteristics while maintaining a responsible accuracy. Types of errors. Quantization error. Quantization error is the difference between the analog signal and the closest available digital value at each sampling instant from the analog to digital converter. Quantization error also introduces noise, called quantization noise, to the sample signal. The higher the resolution of the analog to digital converter, lower the quantization error and smaller the quantization noise. The relationship between resolution and quantization noise for an ideal A by D converter can be expressed as signal to noise, which is equals to minus 20 into log 1 by 2 to the power n, where n is the resolution of the A by D converter in bits and S by n is a signal to noise, which is expressed in dB. This relationship can also be approximated as S by n equals 6 into n. Typical S by n ratios for ideal A by D converters are 96 dB for 16 bits, 72 dB for 12 bits, and 48 dB for 8 bits. Simply, quantization is a process by which an analog signal is approximated to one of the sets of values meant to represent a signal. Rounding or round-off error. A round-off error is also called rounding error, is a difference between the result produced by a given algorithm using exact arithmetic and the result produced by the same algorithm using finite precision rounded arithmetic. Rounding errors are due to the inaccurate representation of real numbers and the arithmetic operations done with them. If an analog signal is assigned or approximated to a quantization level value which is higher than the original analog signal, then the error incurred is known as the rounding or round-off error. Truncation error. Truncation error is the difference between a truncated value and the actual value. If the analog signal above the nearest quantization level is dropped, then a truncation error has occurred. A truncated quantity is represented by a numerical with a fixed number of allowed digits, with any excess digits chopped off. Hence the expression truncated. Errors in computation. There are errors which can be incurred while performing operations on digital data in the DSP processor. These errors hence come up with during the computation, so they are called as errors during computation. Number format use in digital signal processing can be separated into two categories: fixed point and floating point. These designations refer to the format used to store and manipulate numeric representations of data. Fixed-point DSPs are designed to represent and manipulate integers, positive and negative whole numbers, via a minimum of 16 bits, yielding up to 65,536 possible bit patterns. Floating-point DSPs represent and manipulate rational numbers via a minimum of 32 bits, in a manner similar to scientific notation, where a number is represented with a mantissa and an exponent. Example, ax2 to the power of b, where a is a mantissa and b is the exponent, yielding up to 2 to the power of 32 possible bit patterns. The term fixed point refers to the corresponding manner in which numbers are represented with a fixed number of digits after and sometimes before the decimal point. With floating point representation, the placement of the decimal point can float relative to the significant digits of the number. For example, a fixed point representation with a uniform decimal point placement convention can represent the number 123.45, 123.4.56, 12345.67, etc., whereas a floating point representation could in addition represent 1.234567 or 1234566.7 or 0.000012345667, etc. As such, floating point can support a much wider ranges of values than fixed point, with the ability to represent very small numbers and very large numbers. With fixed point notation, the gaps between adjacent numbers always equal a value of 1, whereas in floating point notation, gaps between adjacent numbers are not uniformly spaced. The gap between any two numbers is approximately 10 million times smaller than the value of the numbers, with larger gaps between the larger numbers and small gaps between smaller numbers. Overflow error. Overflow error, as stated earlier on, occurs if a result of a computation cannot be held in the accumulator. Digital to analog conversion errors. Typically, digital to analog conversion errors. Typically, digital to analog converters use fewer bits to represent the digital signal from the DSP processors. During this process, the value may be decreased and an error could be found. Q notation. Depending on where the binary position is assumed to be, a given number can be interpreted as several different values. To make programming simpler, we generally use a fixed binary point throughout the algorithm. To easily specify how many bits are used to represent the integer and fractional parts of the number, we use a notation called the Q format. For example, to specify that we are using 3 bits for integer parts and 4 bits for the fractional part, we may say that the numbers are in Q3.4 format. For example, another possible notation is to specify only the length of the fractional part. This is based on the assumption that the word length is known for a given processor. For example, when working with a processor which has a wavelength of 16 bits, we may simply say that we are using the Q15 format to represent the numbers. This means that we are putting 15 bits to the right of the binary position and 1 bit to its left. In this case, the Q format is equivalent to the Q1.15 format.